Assalamualaikum warahmatullahi wabarakatuh. Welcome to my presentation in 60 arm robots. For this task or this assignment, I'm going to explain you about the models for making a conversion from the kinematic forward and Jacobian inverse matrix. So what exactly this both explanation like the kinetic forward and the Jacobian inverse? Well, technically the inverse and the Jacobian is for visualization of allow the path for allow you to compute where is the end of the arm robot to be exact position in the matrix and giving the path planning for the robots where we will going and trajectory like that. And the Jacobian is like the reverse of it. So also is tracking end and then calibrate where it's going. Example, if we are having a circle, you want to make a circle like in this place, the robot's over here. The Jacobian inverse can actually track the position of the the position of the circle and translate them to the movement or the maneuver of the arm robot. So that's basically the purpose of it. So the fourth kinematics is a formula which actually have a matrix inside. It has, in this case, because we have a 6 DOF robot, degree of freedom, we have DH or definite Hindenburg. It's a calculation. So there is a for component is a angle, degree, and the distance and the length, the length of the length, and the angle between two axes from Z on the Z. So mostly the transform homogeneous will be like this, the transformation. And so because we have 6 of them, we're gonna need 6 of them in total to have this transform. And this is one of the way to implement it using a program to apply it to C. And the Jacobian in the inverse school view looks like this. So as you can see, there will be like more than one here. This one is for link 1 and link 2 to link 6. And there will be 1, 2, 3 times 1, 2, 3, 4, 5, 6, 6 times 6 like that. So it will be square. And to inverse it, can use the pseudo first. And one way to apply it, there is this C. You can use actually something else for this. In this case, it's a simplification of this. Now integration something like that. But I'm not gonna use the whole thing here because a little bit much different than this. And some like the in kinetic forward kinetics much more complex because in this 60 OF. Like in this one is much more simpler version, but inside here is everything here. So to apply this, we're going to the program. Now, we have the same program that we already uploaded before in the last video. And this one is like the developed version of it. So we have some new declaration here for the center X, theta. This one is for getting the circular motion that we will make. And a placeholder for X target and X current. This one is for the end effector, the position. So it will read the position at the end of the arbor. This is all the same. Now we have more new one here. It's just a display. Nothing new here. So here is the multiplication of 4x4 matrix. This will actually be used just a calculation here, just a mathematic calculation, and will be used in here. And here's all of the formal kinematic calculation, and there will be have the endpoint like this. So it's gonna read the x, y, and z axis. So all the calculation. And this is the Jacobian inverse, much more simpler, but it will be useful for tracking down the trajectory. For now, we don't really have any trajectory. We have a forward kinematic target from the arm robot to move the direction or trajectory of that we want. I will show you after this. And this is inverse kinematic. And I calculate the target. And the last one is just circle. In this case, I want to make a circle of a thing for a target trajectory. And then we're just gonna display it. Well, it's supposed to be a display here, but it's not yet ready for the application right now. There might be some things a lot of need to be done before actually can be used there. Other than that, yes, this is the other modification. So when I press R, they will make a target radius on the theta on the before, and then call the inverse kinematic, and make a draw line and make a circle with a resolution of 0.05. And yeah, it will going rotate after reset the circle, it will actually rotate. Other is just the same. It's the same. This one, not different, and still not. It's okay. That's all the program. Now we can run it. So here is the last part, the last one that we already made. Now, if we press 1 and 2, you can see there is a movement here. This like this. And you can see the end effect is actually changing. This is the trajectory. This is the example of it. Now, if I press, oh yeah, also I haven't actually giving the arm robot the limit that they say they want it to be here. This one. It's because well, it must be much easier to actually have the robot arm itself to be programmed with it. I mean, if I do can make the program itself, but it's much more easier to see how it actually goes, and this mostly embedded in the microcontroller. Even though we can make the limit for it, well, you can use it in the mirror on the microcontroller. We still need to modify this. For now, we're gonna use what we have right now. Let me just exit this again. Wait one more time. Still same one. So you can see there's an update there. Now when I press R, it's going to this position, which is about maybe 1.1. I'm guessing it says on the X and Y axis. And then they will make a rotation like this. So you can see, oh no, Y 1.1 is X and Z. The Y axis is on the 0. So they're just making a 2D plane of circle on Y axis. So as you can see, the motion captured to make a circle is like that. I'm trying to make a 2D plane for this, but it's not yet like ready for the presentation. However, you get the idea. The presentation for this is to prove that there are an kinematic and kinematic forward and the inversion of Jacobian to track the end and the trajectory of the robot. That's all did. Yeah, so it's working for now, and yeah, you can see there is the changes on here and the end effector position. And if I release the R, it will stop like that. And it's just gonna changing if I just press. I still can control the robot. It's actually still controllable like that. And you still see it's different. Y axis too, like so. I think that's all the presentation that I need to make. Mungkin sekian end the video. Assalamualaikum warahmatullahi wabarakatuh.